In a previous video, we advanced the possibility of a relation between symmetries of the Lagrangian and the existence of constants of motion. In particular, we showed that for every cyclic coordinate in the Lagrangian, there is a constant of motion. And we also argued that for every cyclic coordinate, there could be a symmetry of the Lagrangian. That was true for the simple class of Lagrangians we were dealing with. In this video, we are going to generalize this and close this relation by showing that for every symmetry of the action, which is something a bit more general than a symmetry of the Lagrangian, there is a constant of motion. And this is the content of the first Noether theorem. People often refer to this theorem as just the Noether theorem, but basically because often the existence of a second Noether theorem is ignored, and the second Noether theorem is also very important, I would say, that fundamental in theoretical physics. Let's prove this theorem in the simplest setting. In this setting, there is a system described by some variables xi, and with a Lagrangian L, which is a function of the xi's, its time derivatives or velocities, and maybe on time. Then we are going to consider infinitesimal variations delta xi such that the variation of the action, when you vary the variables in this way, vanishes. Okay, this looks similar to what happened when we derived the Euler-Lagrange equations of motion, but there are several differences. Okay, we are not saying what are the boundaries here or the limits of integration in the definition of the action. We are not assuming anything about the boundary conditions of these infinitesimal variations. So when we derive the Euler-Lagrange equations of motion, we assume that on the boundary, that's on t0 and t1, these variations vanish. Here we are not going to assume this at all. And here it's not that we are considering a lot of possible trajectories which are differ by some delta xi, and then we are going to take the one that satisfies this property. That's not the thing. The thing is that we consider the action, okay, in general for a generic xi, and then we modify this delta, these xi's with some with some infinitesimal delta xi, and then we find that this is the same. Sorry, this is s of xi, without assuming anything about the boundary conditions of delta xi, and without assuming that this xi is a solution of the equations of motion or anything like that. Okay, this is what this delta s means. Another observation which is important is that we are only varying the variables the variables xi, not the time, which is the parameter on which the xi's depend. Here, delta t is 0 by assumption. This is important because when we take into account that s is the integral over time of the Lagrangian, then if we vary the action, then there is no d of delta t or anything like that. This is just the integral of the variation of the Lagrangian, which means that in this simple setting, clearly delta s is 0 if and only if delta L is 0, because we haven't assumed any particular boundary conditions. This integral has no particular limits of integration, so delta s is 0 if and only if delta L is 0. So in this simple case, you don't see why I am asking for a symmetry of the action and not just of the Lagrangian. Okay, in this case, indeed, these two things are equivalent. We will see that in more general cases, This is not true. What matters are the invariants of the action, but okay, this is what happens in this simple case. And okay, we just have to compute delta L. Now delta L is something that we have computed before, okay, although we did it with the intention of finding the Euler-Lagrange equations of motion, and in the end, after we varied L, we use the boundary conditions of the delta xi's, etc. The calculation initially is just the same, and you get delta S, delta xi plus a total derivative with respect to time of partial L partial x dot I delta xi. Okay, if you don't okay, before this delta S delta xi, remember that is just the Euler-Lagrange operator. X dot I. So these equal to 0 are the equations of motion. This is an important relation that we must remember. So let me frame it, because we may need it later. Okay. It is good as an exercise to remember how one reaches this result, or how one makes this computation, how the different assumptions that we have made on the variations play a role. So let me just do it quickly. I treated these variations as derivatives in this, and then I apply the chain rule. So the L depends on the xi's, so I take the partial derivative with respect to the xi's. It also depends on the x dot i's, okay, and it also depends, or may depend, on time. But since we assume that this is 0, this last term doesn't play a role. And now this term is delta d dt xi, and because delta t is 0, delta and the derivative with respect to time commute, and we have d dt delta xi. Okay, this term, now the derivative d dt is outside of the variation, and we can integrate by parts. The first term stays as it is, because this is not affected by the integration by parts. Then this is the derivative of the product partial L partial x dot I delta xi minus the dt partial L partial x dot I delta xi. I collect the terms that are proportional to delta xi, and then I have the total derivative, and this is just the result that I wrote above. Okay, in the box. Now we have to use the assumption that these delta xi's are very special, and they are such that delta S is 0, so delta L is 0. So for these symmetries, so if these delta xi's are symmetries of S and L, we find that this relation is 0. The right hand side of this box is 0, and let me write it in this particular way. So it's just the same relation. Sorry. dt partial L partial x dot I delta xi equal to minus delta S delta xi delta xi. I could again put this in a box, but before I do this, okay, observe that the right hand side is a total derivative with respect to time, sorry, the left hand side, while the right hand side is proportional to the equations of motion. So suppose that my xi is indeed a solution, okay, then for this particular delta xi's, okay, this right hand side would always vanish, and then I could have some sort of conservation law. Okay, I could obtain that the derivative with respect to time of this object would be 0. This is almost enough, and this is almost the result. Okay, this because we are obtaining for delta xi symmetry, and if the equations of motion are satisfied, we have conservation law, but we have to be a bit more precise. These delta xi's, okay, in general, these are infinitesimal transformations. They depend on some infinitesimal parameters. For instance, we can consider translations of the xi's. So translations of the xi's are shifts by a constant, so it's xi plus some constant. The infinitesimal version of this is xi plus an infinitesimal constant, and delta xi could be just this infinitesimal constant. Let me call them alpha i's. In this case, in this simple case, I would have that the t, since these are constants, okay, I can take these alpha i's outside of the derivative, and so this, in fact, and in this right hand side I can also take as a common factor this xi, and I get this equation. Now this equation is true for any values of the alpha i's. This means that the coefficients of the alpha i's must be 0. Okay, so this equation has to be satisfied. So I can, for instance, reach this result by saying that alpha 1 is 1 and the rest is 0. Then I get this equation for I equal to 1, and so on. Okay, so from this I get that this is satisfied for each I. And then if the equations of motion are satisfied, so delta S over delta xi, which remember is the Euler-Lagrange operator, is 0, then delta partial L with respect to partial x dot I is a conserved quantity, and this is the old result that we got. Okay, this is the conservation of the momentum. In general, okay, this is too simple. There is the alpha i's, and they do not multiply anything. But in general, what you are going to find, and we will see an example soon, is that these delta xi's are some parameters, okay, not necessarily with this index I, but with an index that A, which labels the independent parameters of these transformations, whatever they are, and some factors which are independent of the xi's. Well, the reason why this is so is because these parameters are infinitesimal. We are always staying at first order in these infinitesimal parameters. Then if this delta A xi depends on alpha a, then you could get 0. So it's just these infinitesimal factors, okay, infinitesimal, and these alpha independent factors. Okay. For instance, in this case here, you have some independent factors. You can always rewrite this in this way. okay, and you could say that you have some variations delta j xi, and this would be your parameter a. This happens very often, that in these transformations that involve parameters with indices which are the same parameters as the variables. For instance, this could be if these variables are the positions of a particle in 3 space dimensions. This is just a bit confusing. It looks like it's at the same time a space index and also one of these labels. But okay, in time you will get used to this. Okay. So in this general case, and this is the general case, you have some alpha a's infinitesimal and also plus t independent. This is also important, they are constant. Okay, you go through the same reasoning. You take this alpha a's as common factor and you get the dt partial L partial x dot I delta A xi equal to minus delta S delta xi delta A xi. Okay, this means that this identity will be satisfied for each of these indices A. We could remove this common factor, and this would be the general result that now we frame. Because now, if the equations of motion are satisfied, so this delta S over delta xi is 0, you find that you have these quantities that we can call PA, because they are like the conserved momentum, that are conserved. They are constants of motion because their derivative with respect to time is 0. So if delta S with respect to delta xi is 0, okay, when the equations of motion are satisfied, we will also call this on shell. Okay. Then you have that P dot A is 0 for all these indices A. As many conserved quantities, as many constants of motion as independent parameters in the transformations. So now let me consider a less trivial example. Okay. This example consists on transformations. Okay, we are still with the free particle, and I consider these transformations. Alpha j xk. Okay. They look a bit strange, but I will explain what they are later. Just accept them for the moment, and let me also explain what this epsilon ijk is. This is a completely antisymmetric tensor. It's a tensor only in space indices. This means that if I interchange any of its indices, then I get a minus sign, any pair. Okay. The ik, this is also equal to minus epsilon ikj, and it is also equal to minus epsilon kji. So if I interchange any two indices, this gives me a minus. Also, when 1, 2, and the indices ijk take the values 1, 2, 3, this takes the value plus 1. Now, with this is enough to know all the components of this symbol, because first of all, because it is completely antisymmetric, if any two indices are repeated, so for instance, what is the component 1, 1, 2? Okay, because of this property. If I interchange I and j, I get a minus sign, then this is equal to minus epsilon 1, 1, 2. This means that it has to be 0. Okay. The same happens for all the components that have an index repeated, because I can apply this property or this property or this property. So with indices repeated, I get a 0. Then the only possibility is that the three indices are different. See, these indices vary from 1 to 3. Then the only possibility is that is 1, 2, and 3 in any order. Now, epsilon in this order 1, 2, 3 is defined to be plus 1, and any other order you just get a sign which is associated to the permutation. So applying this property, I get that epsilon 2, 1, 3 is minus 1. Applying this property, I find that epsilon 1, 3, 2 is minus 1, and applying this property, I find that epsilon 3, 2, 1 is also minus 1. Okay, there are other combinations that gives you plus 1. You just have to make to consider how many permutations you have to make from 1, 2, 3 to that particular order, the particular order that you are considering. Okay, so now that you know what this epsilon is, let's see, for instance, what happens for delta x1, how it transforms. Okay, so this is epsilon 1, and then j and k, alpha j and xk. If 1 is taken, neither j nor k can take the value 1. They have to take the values either 2 or 3. So one possibility is that j takes the value 2, but then k has to take the value 3. So this would be alpha 2 because it has the same index as j. It's the j index, and x has to be 3. Plus, because this is always a sum, according to the Einstein summation convention, the other possibility is that you get 3 and 2, and this is epsilon 1, 3, 2, alpha 3, x2. Now this is 1, and this is minus 1. So you get alpha 2, x3 minus alpha 3, x2. Okay, you can check that you can do the same for all the coordinates, and this is still confusing. What is the meaning of these transformations? But let's take only one of the parameters different from 0. Suppose that alpha 1 is different from 0, but alpha 2 and alpha 3 are 0, and I want to find what this transformation of the xi's is. So now I have xi, and now it's only alpha 1, so j has to be 1, because for any other value I get 0, and then I get xk. So if I cannot be 1, because then I get 0. So if it is 1, I get 0. x1 does not transform. If it is 2, I is 2, then 2, 1, and the only possibility is 3. So it is epsilon 2, 1, 3. 2, 1, 3 is minus 1. Okay, and x3. So it is minus x3. And delta x3 is epsilon 3, 1, 2. x2, and okay, you just see that you have interchanged this, and because this was minus 1, this is plus 1, so it is plus x2. Now this transformation in which x2 goes to minus x3 and x3 goes to plus 2 is just a rotation in the axis x1. x1 is not transformed, so this is the axis of rotation. So in general, these are going to be infinitesimal rotations in the axis xi, alpha I, sorry. whatever this I is. And if the three of them are different from 0, the axis is just rotated itself. It doesn't coincide with any of the axis of rotation does not coincide with any of the axis of the coordinate axis. Okay, so these transformations are infinitesimal rotations. Now you can see if they leave or not the Lagrangian invariant. So let's the Lagrangian of a free particle. So let's consider the transformation delta L under these transformations. Okay, I need well, I don't need it. This is 1/2. Sorry, 1/2 m, and then I have 2 times x dot I delta x dot I. Now remember that the delta and the derivative with respect to time commute, so you have m x dot I and then the derivative of this delta xi, which is epsilon I jk alpha j xk. Okay, so delete this to avoid confusions. Now we take this is constant and this is constant. They are independent of t, so they can come out of the derivatives. You get m x dot I epsilon I I j k alpha j, and then the derivative of xk, so x dot k. And now okay, you have to focus on these terms. Okay, x dot I x dot k is clearly the same as x dot k x dot I, so it is symmetric in the interchange I and k. However, this epsilon, which is contracted with x dot I and x dot k, is antisymmetric in the interchange of I and k. Whenever you contract a symmetric tensor with an antisymmetric tensor, you get 0, and we can see it easily. So here it is I j k x dot I x dot k. The first thing that we do is to replace the index I and the index k by k and I without doing anything else. So it's just relabeling indices, and these two things are exactly the same. Okay, this is something that you have to think about maybe, but this is easy to understand. And then now I interchange these two. Okay, these are numbers, and because of this property, this property follows because these are just numbers. It's not that I interchange the indices, but I commute this with this, so I don't get any signs. But here I interchange these two indices and I get a sign, so I get a minus epsilon I j k and then x dot I x dot k. So this is equal to minus itself, so it means that it's equal to 0, and this means that this is equal to 0. So delta L is 0 for all these alphas. Then I just apply, okay, first of all, I haven't used the equations of motion. Also, these transformations do not satisfy any kind of boundary conditions. They don't vanish at given times or anything. If they vanish at some point, it's just by chance. It's not related to the vanishing of delta L. So let's apply this theorem, but first I need to identify the alpha independent part of the transformations. So I write delta xi is this alpha j delta j xi. Again, we have the coincidence that this the index a is again a space index, but okay. So what is this delta j xi? Just by looking here, okay, is the alpha independent part of the transformation. So this is epsilon I j k x k. So that's all I need. And then I know that there is a conserved quantity of this form that I call Pj. More precisely, I should call Lj, because I know that it's going to be the momentum, the angular momentum, that customarily is called Lj. This would be the three components of the angular momentum, and they are like this. So this derivative is just mx dot I, and this is epsilon I j k x k, and this is Lj. So it is proportional to m. Maybe we can rewrite it m. If I interchange these two, it's epsilon I k x dot I x k, and then I get a minus. Okay, this minus is really not something to be worried about, so we can interchange I and k again, and we could write it like this: epsilon j k I x k x dot I. Probably you are not used to see this quantity written in this way, but you have to learn this identity. So suppose that they have two vectors, ai and bj, three-dimensional vectors. So indices that go from 1 to 3. So I can also use this notation, a and b. Then all I need to know is that the vector product of a and b, okay, is another vector with indices I that take values 1, 2, 3, and this is given by epsilon I j k a j b k. This is something to remember if one wants to translate certain identities written with indices into identities written in this vector product language or whatever. Then you see that this is just m, then this is x times velocity, and this is the component I. Okay, but if I don't write the components, the component j, and this is L, which is probably the form in which you have learned to write the angular momentum as the vector product of x and b. And if you write the component j, then you write the component j. Here I'm not distinguishing between indices up and down. Okay, so this is why I'm a bit sloppy, but here the only metric that plays a role here is delta ij, but delta ij is positive, it is the same as the inverse, so we don't care very much about the position of the indices in this three-dimensional setting. So this was we have seen the proof of the first Noether theorem in the simplest setting. So a generalization of this simplest setting would be to consider the possibility that delta S is not exactly invariant. So when I perform this transformation, this infinitesimal transformation delta xi, then what can happen is that delta S, instead of being exactly 0, is a total derivative. So it will be something like this, always proportional to variations of the xi's. So in this case, the theorem is generalized as follows. You go through the same reasoning, okay, and you find that this is dt, this in calculation. Now this is delta sorry, dt delta L. Delta L, remember that it was delta S, delta xi, delta xi, plus the total derivative dt partial L partial x dot I delta xi. But now, okay, by assumption, instead of 0, this is going to be dt and this total derivative. And okay, then what do we learn from this? We can take this to this side, and we find that this integral xi delta xi, well, we can combine this with y delta xi, and this is equal to 0 for any interval of integration, which means that the integrand must be 0, and we arrive to the conclusion that the dt, okay, xi minus yi delta xi is equal again to minus delta S delta xi delta xi. And if I parameterize this delta xi's with some parameters alpha a, then I get these identities for every a. Again, if the equations of motion are satisfied, I find that delta S delta x dot I minus y delta a xi, which I call p a again, is conserved. So the thing is that this conserved quantity, or this constant of motion, which is sometimes called a Noether charge in this context, is conserved. And this is the first generalization of the Noether theorem.